Now let's put the merge sort theory into the actual Java code. Let's see how it's going to work. Let's implement it. So first, we want to have a variable called n. I'll just call it n, which is the length of this given input array, since I'm going to use this n many times. So first we want to check if n is smaller than 2, which means it's either 0 or 1. Then we can simply just return array because it's either 0 or 1 element. We don't need to do any sort. Next, what we will do is that first step, divide and conquer. First step is always divide. So we want to divide into half, right? So we'll create a variable called middle. This mid is n divided by 2, and then we'll divide this original input array into 2 parts, 2 halves, right? So we'll have a left side, which is called left, and then the length of this is going to be mid, and the other one is called right, and the length of this is going to be mid minus n minus mid. I hope this makes sense, because say n is 4 or n is 8. 8 divided by 2 is 4. So this one is going to be 4 and this one is going to be 4 as well. But just in case if n is an odd number, say n is 9, 9 divided by 2 is going to be 4. So this left half is going to be 4, but this right half is going to be 5. So the lengths of these 2 subarrays may not always be equal. So that's why we need to use n minus mid here. Then we'll assign the original input into these left and the right. So these are the temporary arrays. So we'll talk about space complexity in just a few minutes. Now we'll assign this from 0 all the way up to mid. We'll assign this to the left subarray, right? This is, we will fill the left subarray from the given input from 0 index all the way up to the mid index. This is how the left subarray is going to be filled. Next, what we'll do is we will fill the right subarray. Instead of starting from 0, we should start from mid. I is smaller than n, which is the boundary of the original input length. Now, right is going to be I minus mid, because the right index will always start from 0. But since this I doesn't start from 0, we need to minus mid. And then this array is I. All right. Now, since we have divided this original input into 2 halves, are they divided into individualized items already? No, it's not. This is the base case of the merge of this recursion, right? So we need to continue to divide. So we need to continue to divide left subarray and right subarray. As we saw in the visualization, we continue to divide until these items cannot be divided anymore. They are individualized, just one item in that subarray. All right, left and right. Then after this, at this moment, what we will do is that we will implement the merge function, which is a critical function in this entire merge sort algorithm. Now let's see, what do we need? We'll take the original input array, and then we'll take the left subarray and right subarray, and we'll also have a boundary for the left and the right. The boundary for the left subarray is going to be mid. The boundary for the right subarray is going to be n minus mid, right? And then in the end, we'll just return array. So now let's implement this merge function. Right, yes. This one is left, we'll call it left boundary. This one is right boundary. All right. How we can implement this merge function is very straightforward. Since these 2 subarrays are already sorted, right? We can just put them into the correct order of the merged array. That's it. So what we'll do is we'll initialize 3 indices. First one is called, we'll just call it left index, start from 0. Second one is called right index, we'll also start from 0. Third one is called array index. This is the final merged arrays index, always start from 0. So we'll have 3 while loops. The first while loop is when both subarrays are not empty yet. So what we will have is left index is smaller than left boundary, and right index is smaller than right boundary. In this case, what we will do is we will, as I said, we will compare the two front elements of each of the sorted subarray. So very easy. What we will do is, so if left index is smaller than or equal to, you can be exactly small or smaller than or equal to, it doesn't matter because they are equal. And then right index, if this is the case, we will use the left side. So assign this array index, that increment it, and then left index, increment left index as well. Not equal, it's a sign, right? This is when, because this is the front element in the left subarray is smaller than or equal to the front element at the right index, at the right subarray. So we will assign the smaller one, which is the one in the left subarray, to the final merged array. Otherwise, we'll use, let me just copy this. Otherwise, we will use the right index in the right subarray, right? This is the case when both sorted subarray are not empty yet. And if this condition doesn't hold, that means either one of the sorted subarray is already empty. What are we going to do? Very easy. We'll just fill the remainder of the one sorted subarray that hasn't been emptied yet into the final merged array. Okay, so we'll do this. While left index is smaller than left boundary, we'll continue to, just copy this, continue to assign the left front element into the merged array until the left boundary is reached. So similarly, we can do this for the right index and smaller than right boundary. What we will do is we'll keep incrementing right index until we reach the end of the right subarray. That's it. This is the entire algorithm. Now let me quickly hit run and to see if there is any compile errors. All right, it works. Before sorting, it is this. After sorting, is 1, 2, 3, 4, 5, 6, 7, 8. Correct? All right, that's the idea of merge sort and how we can implement this. Now let's talk about time and space complexity. Time complexity for all three cases, best case, worst case, and average case, it's always going to be nlogn for merge sort. That's why merge sort is pretty stable and the performance is very predictable, because we always divide the entire input array into two until we can compare the two individualized items, and then eventually we merge. This merge function takes on time because the two sorted subarrays are already sorted, right? So we can simply compare the front elements. This merge takes on time. How about space complexity? Space complexity, think about, we always have the temporary subarrays to hold the elements, right? So we always need on extra space since we always create temporary arrays in every recursive call. Alright, that's about merge sort. I hope this video does help you understand. I have published the actual Java code into my GitHub. I'll put a link to my GitHub of this merge sort code in the description box below. Please definitely check it out and play around with it so that you can have a better and deep understanding of how merge sort really works. If you find this video helpful, please do me a favor and hit the like button. That's going to help a lot with the YouTube algorithm. And of course, don't forget to subscribe to my channel, as we're going through a lot of classic interview and data structure problems and also LeetCode problems to help people better prepare for their upcoming coding interviews. That's it for today's video. I'll see you guys in the next one.